Before we go on and do some more problems with the change in Gibbs tree energy, I want to remind you about something that I said earlier. When it is true that when delta G, the change in Gibbs free energy, is negative, we call that exergonic. And it is true that when that is negative, it is spontaneous, a spontaneous process. But the reaction is not necessarily fast. And the reason that it's not necessarily fast is that for a chemical reaction to occur, the reactants usually go through an activation energy. They need an activation energy to go through a transition state that is not very stable. So in other words, even though the net change in Gibbs free energy may be negative, they have to first go through an unstable state. And this is where it can take time to get over that step before they can release that energy. So anyway, just keep that in mind, that it doesn't necessarily mean that it's fast, it just means that it's favorable overall. You'll see that sometimes we do things to make this hill less, like a catalyst does that, so that the reaction can occur faster. Okay, and we put together the enthalpies and entropies on an example to come up with Gibbs free energy, but wouldn't it be nice if we just had tables of Gibbs free energy and we could calculate the Gibbs free energy for the reaction using those instead? And we do. So let's look at an example. In this example, we're given our Gibbs free energies, and we're going to basically just subtract products minus reactants. And again, we're using the coefficients. So is this reaction spontaneous? Yes, negative for a change in Gibbs free energy is spontaneous, so this is spontaneous. And we could also say something else. If we reverse the reaction, in other words, if I had the reaction the change in Gibbs free energy would be the same number opposite sign, and this reaction would be non-spontaneous.